Okay, so hopefully most of you were at the last workshop where we talked about installing Anaconda and using Jupyter Hub and introduced some libraries like NumPy and Pandas and Matplotlib and Seaborn that are at the center of writing machine learning programs using Jupyter Hub. And you'll understand most of this workshop even if you weren't here for the last one, except maybe you might struggle a bit with the code at the end. But so for this one, we're going to delve into some machine learning theory and talk about supervised and unsupervised learning, and then move on to just actually implementing a supervised learning algorithm called KNN. So without further ado, I'm going to start off with supervised learning. So over here, we have a graph that is a scatter plot of outdoor temperature in relation to cricket chirps. And so what a supervised algorithm can do for this is that it can draw a line to connect the dots, like maybe a line of best fit like this. I'm sorry, I can't draw to save my life, so you'll have to bear with me. And so, for example, if you want to determine the number of chirps that a cricket does in 15 seconds for a value that isn't recorded here, say, let's, for example, 72.5 degrees Fahrenheit. So we could do that using this line. And maybe we could make a better function for this. So we could have more of a second degree polynomial or quadratic function that goes something like this. And that's probably covering more of the data points. And so would probably give us a more accurate representation of what the value would be from here. That's a very unstraight line, but yeah. So that's quite a silly example, but just to illustrate it in a simple way, there's much more useful uses of this kind of algorithm, which could be for example, if your friend needs to sell their house and they want to determine how much they can sell it for, they could plot a number of data points for houses of varying sizes and then their prices on the x-axis, and then use that and use a regression algorithm to make a function to join those dots and then predict the value for their size of house that they're not sure what the value for that should be. And so this kind of algorithm is known as a regression algorithm. And as you've guessed by now, it's used for predicting continuous valued output. So think continuous functions, real numbers. And so another type of algorithm that comes under supervised learning is classification algorithms. So these are used for predicting discrete valued output. For example, we have a graph here on the right, and so that's tumor size on the x-axis plotted against whether the tumor is malignant, which means that it is indicative of cancer, or if the tumor is benign, which means that it is not indicative of cancer. So benign is the circles over here, and then the crosses represent malignant tumors. And so what an algorithm could do in this case is draw something called a decision boundary, which separates one type of attribute from another type, in this case, benign from malignant. So this would be a good place to draw the decision boundary. And so anything on the left of the decision boundary would be considered benign, and anything on the right of the decision boundary would be considered malignant. We can also represent this in a slightly different way with binary discrete input, like ones and zeros. So maybe ones could be benign, and then zeros could be malignant. So you could sort of just drawing this over that. I hope that makes sense. So that's another way that we could draw this. And it's not necessary to just have two possible outcomes for this. So instead of just being benign and malignant, we could also further classify it in terms of type of cancer. So it could be type A, type B, and we could have multiple values for that, 1, 2, 3, 4, or different symbols for that. So then for classification, we can also classify based on not just one attribute, like it was in this slide where we have just tumor size. We could, to get a more accurate prediction, we could classify using multiple attributes such as tumor size and age. And so for this is the decision boundary here, and then we've got benign tumors on this side, and then malignant tumors above the decision boundary. And so if we have something on this side that we need to classify, then an algorithm can predict that that's probably, thankfully, going to be benign. And then, unfortunately, if something's on this side, then it's probably going to be malignant. And then we have algorithms that can determine not just based on 2 or 3 attributes, but theoretically just an infinite amount of attributes. And that kind of algorithm is called an SVM. And we're not really going to delve into that for this workshop, but just in case anyone's curious about that. Sorry, my screen's just stuck here. Okay. So those were examples of supervised learning, and now moving on to unsupervised learning. So with supervised learning, the data that you input tells the algorithm what the right answers are. So for example, with the example of the tumor being malignant or benign, the computer knows that these data points represent benign tumors, and then the data points more towards the right represent malignant tumors. And so they know the right answers with that, and they know what to classify and what the labels are. But when it comes to unsupervised learning, you just have data points thrown in to the computer without it knowing what the different labels are. So everything's just gray, and the computer needs to figure out how to cluster them together and what label to give them. So that's just an example of how an unsupervised learning algorithm would cluster these together. And so a real life implementation of an unsupervised clustering algorithm that we see pretty much on a daily basis is Google News, that takes hundreds of thousands of stories, and it looks at them and it groups them into cohesive news stories without being told what the specific label for them should be. For example, for this one, so there's a series of these articles, and the algorithm automatically determines that they're all in some way about travel. So this one's about metros, this one is about metros from Times of India, and then this one is about air travel. And then they're all in some way related to a similar theme. And then some other examples are a social network analysis, which, so an algorithm can see the way that you communicate with people using your email or your Google Plus circle or your Facebook friends. And based on that, it can determine which groups of people are and which demographics are connected with each other. And so a very applicable use of this would be market segmentation. So many companies have massive quantities of customer information. And what an unsupervised algorithm can do there is cluster together different types of people into market segments so that companies can make their marketing strategies more targeted towards different personality types and demographics without being told specifically what the labels of those market segments would be. So, and this is an unsupervised algorithm because we don't know in advance what the market segments are. going in or which people will be clustered together. So the algorithm discovers all of this just from the data that's fed into it. And so this is another example of a unsupervised learning algorithm called the cocktail party algorithm. And what this one does is that, so most of you probably been to a cocktail party where there's just a lot of people and everyone's sitting together and everyone is talking at the same time. And very often people are talking over each other. And sometimes it's very loud and hard to distinguish different voices clearly. And so in this case, what we can do is we've got two people, person A and person B. And so we can position two microphones at different relative distances from both of those people. I'm not speaking too fast, am I? Is everyone understanding as I go on? I'm going to take silence as a yes. Okay. Okay, thanks for the thumbs up. So we have person A and person B. And for example, we got two microphones and we positioned the green microphone that's closer to person A and further from person B. And then the blue one is closer to person B and further from person A. And so in this case, we can imagine that the green microphone will pick up person A's voice louder, and then the blue microphone would pick up person B's voice louder. And so we're going to show you what the sounds would be from these recordings. Rakshit, can you play that?
Yeah, sure.
One, two, three, cuatro, cinco, seis, siete, ocho, nueve y 10.
So it's not a very interesting cocktail party conversation.
1, 2, 3, 4, 5, 6, 7, 8, 9 y 10.
Okay, so you can probably tell that.
1, 2.
Yes, so you can just tell that microphone 1 picks up the English counting better, and then microphone 2 picks up the Spanish better. So yeah, you can go on with playing that, but
3, 4, 5, 6, 7, 8, 9, 10.
And so what the algorithm does here is that, okay, we can just go through with playing the second one, and then I'll explain.
2, 3, 4, 5, 6, 7, 8, 9 y 10.
All right. So what happens over here is that these two microphone recorders, when we give the recordings to an unsupervised learning algorithm, the algorithm finds a structure in this data, and then what it will do is it listens to these audio recordings and say, it sounds like two audios are being added together or that they've been summed together to produce these. So it can separate the two different audios and then produce outputs that have one and the other clearly separated from them. I'm just going to share screen again. Yeah, and so this is an implementation of the cocktail party algorithm using Octave. That's just one line. So it's not a simple implementation, but it's just to demonstrate that it might seem like it might be a lot of lines of code, but in this case, it can be implemented in just one line. Not to say that it isn't a complex intuitive understanding behind that. Okay, so now we're going to talk about a very important practice when it comes to making sure that your machine learning algorithm is working. and that is called train test split.
We can't hear. Oh, sorry.
Can you hear me now? Can everyone hear me? Yeah?
Yeah, I can hear you.
Yeah. Sorry.
Yeah, all good. So with that, so what you want to do is you don't want to use all of your data just for training your model, because what can happen with that is that your model might take in an input and give an output, and you have no way of knowing whether that's correct. Unless you have that classified before in your data set, which is why you should split your data set and have a holdout sample so that you can put that back into the model as input and see if the output that you're getting is the output that you expect to get. So, and there's a cute meme to demonstrate that. And so, does anyone here have a YouTube channel? This isn't, I'm going to explain this anyway, but it would be more interesting if somebody does. I can't see the chat for some reason. Okay, I'm just going to try this. So suppose that your friend has a YouTube channel, and they're run a YouTube channel during the day and they're data science at night, and they have a clever idea to see how positive or negative their reviews are without needing to go through and read every individual review. So what they do is that they plot a data set, and these are all the data points for positive reviews and negative reviews. And so what you can do with that is if you make a machine learning algorithm and the decision boundary that they've calculated that wrong somehow, and they get a decision boundary, like say here, and like we should all know by now that the actual boundary should be somewhere about here. And now if they haven't split their data, what's going to happen is, and if they don't have a testing data set, what's going to happen is that there's no way of them knowing that any values that they get here, which are being classified as negative reviews, should have actually been positive. And they're probably slowly going to sink into depression, wondering why their hard work is going to waste and people aren't happy with their videos. And so that's why you should implement a testing data set. Okay. And so we're just going to introduce another library here called scikit-learn. And we're not going to get into a lot of features with this, but we're going to use this for the code at the end. So it's just another open source library that is used for building statistical and machine learning models. And it's built on NumPy and SciPy and Matplotlib, two of which we went into the details up in the last workshop. So now we're going to talk about an actual implementation of a supervised learning algorithm known as the KNN algorithm. And so what KNN stands for is K nearest neighbors. And this is known as a lazy algorithm because it doesn't predetermine a function to figure out, it doesn't learn a discriminative function from the training set. So all of the processing happens in real time. And some of you might have your spidey sense tingling as to what a major drawback of this is, but we'll discuss that in a later slide. And so just going to mention that what K stands for over here is a parameter that refers to the number of neighbors to include in something called the majority voting process. And if you don't understand what that means, that's fine. We're going to explain that in the next slide. So over here, so I'm just going to demonstrate using this here how the algorithm actually works. So if you feed your data set in and all of these values are recorded. So there's a Squirtle here and 2 Squirtles and a Charmander. And now if this is the input that your algorithm needs to classify, what it's going to do is that it's going to see what the majority of the nearest neighbors are. So that's what's called the majority voting process. And then based on that, it's going to classify what the input is. So in this case, the input would be another Squirtle, because there's 2 Squirtles opposed to 1 Charmander. And so with this, how you pick K over here, which is K is the parameter for the number of different objects that you consider when you make this decision. So why K is important, and K can change the output that you get. For example, if you have K equals 3 over here, you have 2 Squirtles and 1 Charmander, so this is going to be a Squirtle. But if we move on to the graphic on the right, and if we consider K to be 7, then we have a much larger number of objects that we're considering in our decision-making process. So we would then have 3 Squirtles and 4 Charmanders that are closest to the point in the middle. And we would then classify this as a Charmander. And so how do we decide what value we should give for K? So that's actually pretty simple. You would consider the total number of attributes that you have in your data that you're feeding into the program. So in this case, that would be about 9 attributes that you're putting in. And then you would just take the square root of that. So for this case, square root of 9, 3 would be a good value to take for K. And then another thing to keep in mind is that if you have an even number from the square root, then you should add or subtract 1 to that to make that an odd number. Because if you have an even number, for example, let's say K was 4 over here, and so in reality, in the picture, it seems like this one and this one and this one, these are the closest ones, but let's pretend to get the point across that it's these 4 that are the closest. So 2 Charmanders and 2 Squirtles. So now you can't really make a decision based on an equal majority. So there needs to be an odd number so that there's a clear winner for which object appears more closely. So that's how KNN functions. And then in which cases should we use this algorithm? So one of the conditions is that data needs to be clearly labeled. So this is a supervised learning algorithm. You can give in unclassified data in the original data set and then expect the algorithm to figure out how to cluster them together. So it does need to be clearly labeled. And then the other thing, and some of you might have figured this out from the first KNN slide, is that the data set needs to be small. That's because this is a lazy algorithm and all of the processing happens in real time when you execute it. And so if there's a really large data set with thousands and thousands of different values, it's going to take a really long time for the algorithm to run through all of them and then make something like this with thousands and thousands of different attributes. Would take a lot of processing power and time. So yeah, that's why you need to have a fairly small data set. Something in the early hundreds should be fine. And the data needs to be noise-free. So yeah, having noise in the data can be really problematic for a lot of machine learning model implementations. So what noise in the data is, for example, in this case, we have, so we've got color, red or blue, which is fine. Visible flame, so we have a tail flame on the Charmander. That's straightforward as well. But then if we move on to class over here, there's Charmander, that's fine. And then a Squirtle, that's fine. And then we've got two different types of ways to represent the classes that should be labeled as Charmander and Squirtle, right? So that's called noise in the data, and the algorithm's going to struggle. The algorithm's going to consider these as two separate types, and so that's going to be a problem. So you need to have data that's noise-free in this implementation. Okay, so how does the algorithm actually work? Is that I mean, it's pretty intuitive from the more higher level theory that we just discussed, that the way that you would calculate what the nearest neighbors are is by calculating the Euclidean distance of the input point from the other attributes. So you just get these Euclidean distance values for every single one of these during runtime. And so it'll just store all of these values and then find what the smallest values are. And the number of the smallest values that it's going to consider are what your K parameter is, which in this case is 3. And so we already know that just from visually looking at it, that would be these 3 values here. And so those are the 3 values that it's going to consider. And then classify this as a Squirtle. Okay, so now we're going to move on to actually looking at the implementation of this algorithm in using Python.
Hey guys. So let's work with Jupyter Notebook. So first, let's title it as iris dataset. We'll be working with an iris dataset today. And let's first do the necessary imports. And let's add a markdown cell. And then for any machine learning problem, NumPy is a necessity.
Rakshit, people are just opening Jupyter Hubs. Like maybe wait a minute. I think they're.
Yeah, sure.
Yeah, let's just wait
Sure.
a few seconds for them to open it. Does everyone have Jupyter? If you have Jupyter Hub open, can you just put that in the chat so we know how many people have it open? Yep. So Christian, Nick, great. Who's left? Is anyone not? Does anyone not have it open? Cool. Seems like everyone has it open now. Great. You can continue.
So let's continue, guys. So the next import is pandas. And then we need matplotlib. And then for the KNN classifier, we will need to import from sklearn, which is scikit-learn. So from sklearn.neighbors, import k neighbors classifier. And then for the data sets, even sklearn also consists of data sets, so we can import the data set from the sklearn library.datasets. And then from sklearn, we also need train test split, so that lies under model underscore selection. So train test split. And then we need to find accuracy, so that is under sklearn.metrics. And now we import accuracy score. And then let's use this matplotlib inline so that when we store it, the images stay with the Jupyter notebook. Let's run it. So it's taking its time. So let's go to the next block, and now we should get the data. Let's wait for a minute for this to complete running. Okay, so it's a typo. Yep, now it's fine. So now to load the data, we just need to, let's first see what type is load iris. So type of load underscore iris. So we could see that it's a function. So a function might return a value. So let's store it under iris underscore data set. So to see what are the functions, what all are included with iris underscore data set, let's see using this function, director function. So we could see that there's a description, there's data, there's feature name, there's a file name, there's target, which are the labels, and there's target name. So let's first look at the description of the iris underscore data set. Okay, we need to print out for appropriate formatting. So we could see that this is the description. So we have 150 rows, and the attributes are 4. The attributes are sepal length in centimeters, sepal width in centimeters, petal length, then petal width, and the categories of the categories are setosa, versicolor, and virginica. So there's also a statistics of the data which is present. So we could see that the petal length and petal width are highly correlated, and the sepal length is positively correlated but not high, but the sepal width is negatively correlated and it's a bit low. So we have the references mentioned, and we can also see when it was created and all the stuff under description. Now let's see the data. So we could see that it's an NumPy array, and it's not pretty good to read, and it's pretty just numbers. So let's make it understandable and readable using pandas data frame. So let's store it as iris equal to pd dot data frame of iris underscore data set dot data, and the columns is equal to iris underscore data set dot feature names. Let's see how iris is. So we could see that this is so much understandable and readable when compared to this NumPy array. So for looking at the data, we could change it into pandas data frame and make it more visible. And when we change into pandas data frame, we could even see the summary and the summary of the statistics using the scribe method. So when we use this, we could know the number of counts for each and every attribute, and the mean for each attribute, the standard deviation, the minimum value of each attribute, and the 50 percentile, 25 percentile, 75 percentile, and the maximum value for each value. And let's just see the target names and the target variables. Okay, typo. So we could see that the y values, which is the target values, is just numbers 0, 1, and 2. So what is 0, 1, and 2? So we could see that 0, 1, and 2 are setosa, versicolor, and virginica. So 0 is labeled, setosa is labeled as 0, and versicolor is labeled as 1, and virginica is labeled as 2. So we can even find the target names using iris underscore data set dot target underscore names. So we could see that the target underscore names are given over here. And next is splitting the data into training and testing data. So for splitting the data, we'd be using train to split, and train to split releases 4 return values. So which is x underscore train, then x underscore test, then y underscore train, and y underscore test. So this is equal to train underscore test split. We need the first the x values, which is iris dot data, iris underscore data set dot data, and then the y values is iris underscore data set dot target, and the test size is generally used as 0.2. So now let's see how x underscore train is dot shape. So it's 120 into 4. So we could say that 120 divided by 150 is 0.8. So we're getting the training data set 80%, and the shape so proves us that. Let's see how the training data set looks. So the first 5 values look like these. So if you and I, both of us, need to get the same values for training and testing, we could use random underscore state. And if we use the same number, then we both would be getting the same values. So let us use 4 as the random state. And now let's rerun it. And we could see that probably you guys should be seeing the same data set for the x underscore train for the first 5 values. Can you guys see the same values? You could probably chat it out.
Rakshit, just quickly, someone wanted you to explain the above part quickly, like just recap over it quickly.
Yeah, sure. Which part?
The top part, I think. Is it all of it, Apratim or Apratim?
Which part do you want me to explain again, Apratim?
He just wants a quick recap.
Okay, so until now, we've just imported the libraries, and then we've imported the data set. So this is an inbuilt data set which scikit-learn provides us. Then these are the features inside data set. So we could just use the description to see all the description of the data set which is provided by scikit-learn. And then this is the data. So these are the X labels. These are the X values. And we're just making it to a data frame so that it's more clearly understandable and readable. And then we're describing, when we change in the data frame, we can even see the statistics using the describe method. So this is an advantage of changing into a data frame. So this is the statistics summary. For each and every attribute is given the count, mean, standard deviation, minimum, and the percentiles and the maximum. And these are the target values. So these are the Y labels. And these are the target names. And then we've split the data into training and testing. So X underscore train and X test, and Y train and Y test. So we've used test size as 0.2, which is generally being used. And we've set the random underscore state equal to 4 so that you and I will be getting the same values for the X underscore train and Y underscore test, so that the classifier would be predicting this, so that it would give the same results for both me and you, the accuracy score and the other stuff. Was it clear, Apratim?
Cool. And yeah, he said yes. And one more question was, what variables are the percentiles measured on? The ones on the data frame?
Okay, so for each and every attribute, the percentiles are measured on, like, for sepal length, the percentiles are measured separately, and for the sepal width, it's measured separately, and for the petal length and petal width, it's measured separately. Is that clear?
Is that whoever asked, is that clear now? Yeah, great job.
Yeah, cool. So moving on. And did you guys get the same values as me for the training data set? Cool, guys. So after splitting the data, okay, let's see the y values as well for these y_train. Yeah, cool. So these are the y values. And next, after splitting the data, we need to train the data. So let's add a markdown cell saying training. So for training the data, as using the KNN classifier, we would not be sure about which number of neighbors to use. Like as Malayala told, it's generally use the square root of the total values, but it's always better to use a for loop and then find out, plot it as a graph and then find out which gives the maximum accuracy, so that we could use that as a final model. First, let's create a list saying accuracy score, and then using for loop for k in range 1,25, no 1,14, and then let's first initialize the classifier. So this is done using k. Yeah. And here we specify the n neighbors, which is equal to k. And then we use this one to fit our model. So knn.fit, and then we specify the x values, which is x_train, and then the y values, which is y_train. And then let's store the predicted values in a variable called prediction, which is equal to knn.predict of x_test. And for finding the accuracy score, let's store it in the accuracy score list. So accuracy score dot append of accuracy underscore score of, so first is the real values, which is y_test, and next is the predicted values, which is prediction. And let's run it. Cool. So let's plot the accuracy score and see how and which one to use as the neighbors. So plt.plot of AICC_score, and let's show it. plt.show. So we could say that after the n neighbors is 1, and it goes up and it becomes a constant value. So as Malayala said, we could this is one. The number of attributes is one. The number of attributes one. The number of rows is 150. So the square root of 150 is around 12. But we need an odd number, so let's use 11 and then finalize the model. So let's add a markdown cell saying final model. And then let's create the final model. So let's name it as final_model, which is equal to k neighbor classifier, and then underscore neighbor is equal to 11. And then let's fit the final model. So final model dot fit of x_train and y_train. Then let's predict and store it in prediction. Predict of x_test. And let's print out the accuracy score. Score of the model is accuracy underscore score of y_test and prediction. So we could see that the accuracy score of the model is 96%. Isn't that cool? Almost around 97 out of 100 times the model predicts the right value. So it's not readable. Let's just round it off to the closest one using a round function. So round off accuracy underscore score. And let's round off to 2 decimals. So the accuracy score of the model is 97%, which is pretty high for this one. So that's it, guys. Let me know if you guys have any questions.